And so what we're doing, Barry, is we're exploring a series. This is kind of the first of a series of few months long exhibition online.
Mm-hmm.
We're taking Michael Sorkin. I don't know if you knew the late architecture critic who passed recently. He was an avid critic and wonderful inspiration in terms of the public realm and what is the essence of architecture, not necessarily just the built form, but what are the equity aspects of architecture.
Right.
And so there's an essay that he did called 250 Things That an Architect Should Know. And so I'm kind of picking apart some of those things and then exploring them more deeply. So the essay is in the book, What Goes Up? The Right and Wrongs to the City. And so we're going to be discussing how sound travels, and what his phrases were basically, what is the distance that a shout carries and what is the distance of a whisper? And so those are the two things that we'll be exploring. And that's why I thought sound, how sound travels makes good sense for us to discuss.
Sure.
So I guess I would start with just for I think 4 decades, you've consulted on sound in the built environment. And so I wondered if maybe a good place to start is the field recording, because to understand how sound travels, you have to start by observing sound movements. Would that be correct?
It certainly helps, to actually have an understanding of the way things are experienced. Recording isn't necessarily the first step in that, but critical listening is.
Mm.
And that's just spending the time to listen to the way sound behaves in the environment.
Mm-hmm.
Back in my early CBC radio technician days, that's one of the things they taught you about recording, was just listen to the way it sounds, like say a musical group sounds in the space, walk around, and then decide then where you put microphones to capture that recording.
Mm-hmm.
And that's certainly a big part of establishing what a reasonable acoustical environment sounds like.
Mm-hmm. Would you say, so maybe I'll just ask, what's the most interesting field recording you've captured?
Well, certainly that the most unusual one was that recording in the cooling tower at Elma, Washington, the Satsop decommissioned nuclear plant. That was just trippy. Because literally a whisper, like at the quietest you would talk to somebody, say 3 or 4 feet away, it came back to you because it's a perfectly circular focusing field in there. So even the quietest sounds would be reflected back with a sizable delay on the echo.
Mm-hmm.
Very, very trippy.
Yeah. And so the sound is bouncing, or what we might call reverberation. Is that right?
Yeah, and there's 2 aspects to that. There's a direct sound, a first reflection, or multiple reflections, and that would be what most people call an echo. And then reverberation is the sound bouncing around and decaying in level each time it essentially passes by you.
Mm-hmm. So how do we define a reverb or a reverberation time?
Reverberation time is the time it takes for a sound. Usually the most easy way to think of it is like an impulse, like a clap or something, to decay to 1/1,000,000th of the original level. And that's 60 decibels. So by the time it drops to minus 60, that's the decay slope is considered the reverberation time.
Mm-hmm. And so when you were in that cooling tower, what was happening to that sound? How was it decaying?
Well, the interesting thing about the cooling tower is that there wasn't really a reverberant field because it wasn't truly enclosed. There's the little legs that you see in the pictures of those things, and you think, well, how tall can those be? But they're like 15 meters tall. So essentially it's completely open around the bottom and open at the top. So you don't hear reverberation, but you hear repeated flutter echoes that, because it's perfectly circular, they come back at you from all directions, pass through each other, and then hit the walls, and then are focused again. And because the cooling tower is curved vertically, they also travel up. And then sometimes they'll travel back down again.
Oh.
So it is just the strangest sort of surround sound effect for echoes, because they literally swarm around you and then they kind of go up and out the top. And if you have binaural recording, so you actually have a recording system that simulates the human ears, you hear all that spatial differentiation. So you hear where they come from, where they go to. It's very cool.
And what's interesting from the layman's perspective, from someone that doesn't know much about sound, is that when you think about measuring sound, like the question, what's the distance a shout travels, or what's the distance of a whisper, it's not as simple as just taking a measurement of how fast sound travels, but it's really about what do we hear and how audible is it. And so the reverberation and the echo are kind of affecting our ability to hear. Is that correct?
They certainly affect the ability to understand what's being transmitted. Speech is made up of phonemes, syllables and parts of syllables. And if the reflections and reverberation walk on top of those, you can lose the ability to understand things. So as the reverb time increases, and so you're in, anything from a stairwell to a hockey arena, the speech intelligibility is greatly reduced, because now as each new syllable comes along, it's being stomped on by all the other reflections and reverberation. And that's why for designing for speech intelligibility, like in a classroom or a theater, you have to be very conscious about the arrival time, the level of reverberation, the level of reflections, when they come, where they come from. So it's just quite a balancing act in that process.
And so I think you'd mentioned when we talked earlier before this interview about the idea of, we talked about the Elma cooling tower, the decommissioned tower. There was also a room full of clothes that would be that kind of idea of where sound doesn't echo or reverberate that much. So that's the opposite of the cooling tower in a sense. What's the best condition for a whisper?
Well, for a whisper, the controlling element is likely going to be background noise, because a whisper starts off quieter. A stage whisper might be, say, maybe 45 dB at the other actor's location. And because sound drops in level at 6 dB per doubling a distance, at some point, that sound drops down to the level where it matches or is masked by the background noise in the room. So again, for a theater, the goal is to get the noise level down low enough that people can hear something like a stage whisper at a great distance. Outdoors, a whisper gets pretty quickly eaten up by traffic noise, wind noise through the leaves, and that sort of thing. But the sound behaves at a shout and a whisper the same way. When it leaves somebody's mouth, it behaves in the same fashion.
And when one is sending that signal, whether it's a whisper or a shout, it depends on area, where the sound, how far the sound is going. We talked a bit about the field. I wonder if you could bring that in, like with the idea of when one needs to direct the sound of the shout, it can go farther than if it's spread out. Why is that?
Normally, most sound sources have an omnidirectional output or very close to it. So if you're talking, the level of your voice behind you is very similar to what it is out in front of you. So the sound spreads as a hemisphere that's spreading across the ground. Each time you double the radius, you increase the surface area of that sphere by 4 times.
Mm.
So it has a very predictable drop in level. So it would be 6 dB every time you double the distance. So the first, say, if somebody's a meter away and you talk to them at a reasonable level, if they move 2 meters away, it's 6 dB quieter. If they move 4 meters away, it's another 6 dB quieter. Now, once you start to get to really long distances, there's some other factors that come into play, but that's, there's the atmosphere absorbs sound, and that depends on humidity and temperature. But generally, you can think of it in those terms. So that if you want to get somebody's attention who's, say, half a baseball diamond away, you would cup your hands around your mouth to direct the sound more towards them. So it isn't a hemisphere anymore. It's now, say, a quarter of a sphere. You've sort of taken a conical section and redirected that sound towards them.
So you've effectively shrunk the area.
Correct.
Yeah. So just last question back to the whisper. If we were to find a perfect, and I think we talked a little bit about a corner and what happens in a corner. So is a corner a good place for a whisper, or what happens in that corner situation?
Every time you reduce the area that you're either projecting sound into or hearing sound back from, you increase the effective level. The same way as when you cup your hands around your mouth, you tighten up the direction that sound is traveling. If you add one wall, you increase the level by 3 dB. If you add a second wall with a right angle corner, that's 6 dB. If you add the 2 walls in the floor, that's 9 dB. So that's subjectively just about twice as loud. So if you were going to try to project a whisper, the best place to do it is back right up against a corner in a room. And it would actually travel, all the sound, instead of traveling behind you, would all travel forward out of that corner.
Or if you had a secret that you really didn't want everyone to hear, you might choose not to be in a corner.
Yes. Or, there's the other famous aspect of acoustics is whispering galleries. Some of the big cathedrals with the curved ceilings and round construction, that has that same effect as the Alma cooling tower, where a whisper on one side can be picked up by somebody just like you came up and talked to them in their ear across the dome, which is the reason that you generally try to avoid dome-shaped facilities in almost every practical application, because it creates all kinds of interesting acoustic challenges.
Right. So the dome in a performance activity becomes more challenging because it's collecting everything and sharing everything.
And interestingly enough, if you were at the center, everything would come back to you as though you were wearing headphones. And then as you move off center, you end up with a space exactly opposite you where all of that sound is focused. And as you move further away from there until you get to the outside edge, that focal point moves, and then it goes around to a point again on the outside wall where it would literally sound like somebody else has headphones on. So, yeah, it creates some interesting challenges in spaces where that isn't appropriate.
Yeah. Well, I want to thank you. There's a lot more we could go into depth on, but I really wanted just a short little introduction for everyone to hear of our conversation. And I want to thank you very much for your time and for helping us to really think about sound, not necessarily just as the distance. It's not just about the distance. There's a lot more complexity involved, and reverb and echo and shape of surfaces and the number of surfaces. All of those things have a difference. So.
Yeah, absolutely.